Um, yeah, thanks everyone for attending today's talk. I don't know whether I should hold it this way or yeah, it doesn't matter. Okay, so I'm Yukang Yan. I'm an assistant professor at University of Rochester. This is actually my second semester as a faculty member, so I'm relatively new. Um, so if you are curious why there are some Chinese characters there, it's kind of like I did my PhD in Tsinghua University in Beijing, China. And then I did a postdoc at Carnegie Mellon University, HCII. And after that, I joined the University of Rochester. We have a HCI group called Rock HCI Group. And then I also lead my own lab, Bear Lab. That's the link. Yeah, so today I'm very excited to talk about my research that is on how to understand, predict, and enhance user behavior in mixed reality. Before I dive into more research details, I will still want to briefly talk about some concepts that is relevant. I guess we do not need to explain too much about HCI here, but let's just make sure we are on the same page. So I consider human-computer interaction as a bidirectional interaction between the human users and computer systems. There are two directions. On the input direction, it's about how human users can deliver their interaction intents, what they want, to the computer. And on the output side, it's basically based on the recognition of their intents, try to provide the information, feedback, or like the functionality that users want. And then we have the interface as the medium that helps like moderate this communication between the human and the computer systems. And if we look back at the history of human-computer interaction, or basically the computer science, it's also an evolution history of different types of like interfaces. For example, we start with something is more like text-based. We use like command line interfaces to input the commands through like keyboards through like text. And then later we have something more visual, that is graphical user interfaces. And later we also have seen the emergence of like natural user interface. I don't know whether people are familiar with the term of NUI. It was quite popular a few years ago. But basically, it's talking about instead of interacting with like desktop computers, how we interact with different form factors, including wearable devices or smart devices that we think of. And then one thing to mention is that for each of the interfaces, for each of the dominant interfaces at the time, they also comes with their unique interaction paradigms that actually facilitate the communication between users and the computer. For example, when we want to input like text, the command as text into this like command line interfaces, we invented something for example, the text entry techniques. We have different types of physical keyboards. We have different types of text entry techniques that can even support most of our text input today. And then like for graphical user interfaces, we also have the WIM paradigm, which stands for the Windows icons, menus, and the pointer that can support most of our tasks on such GUIs. That's also the case we can use most of our like functionalities on the desktop with WIMP interaction paradigms. And then when people want to find something more natural, they somehow try to mimic how we communicate with each other in the physical world, right? That's when we see more investigation in the area of like multimodal interactions, including voice-based interaction or gestural interactions. That's kind of similar or we feel natural because we use these modalities when we communicate with people. And then that's the past. We're looking towards the future, right? One thing that I have a personal bias about what would be popular or what would be something we'll use in daily life is the mixed reality interfaces. So it's really hard to predict for the future, but if you see the trend, right, we try to somehow move from the pure digital text or GUI-based interaction to more and more the integration of the physical and the digital world. So from that sense, I feel like mixed reality interfaces actually is a good fit in this trend. And then what we want to talk about today is not whether mixed reality will be the future. We want to talk about if mixed reality will be something we'll use in our daily life, what might be the interaction paradigm that can uniquely support it. Before answering that questions, I will still like try to give some definition or like about the term. The first thing is mixed reality because you see augmented reality, virtual reality, extended reality, mixed reality, or like metaverse if you still remember that term. So there are so many different terms relevant to this kind of technology. Here, the definition I adopt is defined by Milgram of quite a while ago. So when I refer to mixed reality, it's not a specific technology type. AR or VR is kind of a spectrum from the very real world to the very virtual environment. So here I want to give a little bit more explanation. The real world is the physical objective world that we're in, even not the perceived physical world, right? On the other hand, is the virtual environment. It's pure virtual. It's purely fully immersive. You are not even aware that you are in a different world than your body. Physical, you can think about the Matrix movie. That's the most close example I can give. Is this way you are not aware that your mind is in a different digital world. And then on this spectrum, we have something that we are more familiar with. For example, the augmented reality, where like the majority of the things you see is the physical world, but you can still render some digital component. You can register like these digital widgets or interfaces in the physical world. You can interact with them in a similar way with like your touch, the physical objects. And then on the other hand, it's not accurate, right? As we said, it's not really virtual environment, but VR is closer to the other end. Is everything you see is rendered by the system, but you are not super immersive because you know you are wearing this heavy headset. You are seeing something that is rendered. And like going beyond just like AR and VR, there are something that people are not so frequently talking about is augmented virtual reality. Or here I see a very close example is the see-through AR, right? For example, Vision Pro. You see the physical world rendered by the computer, right? The video streams are captured by the front-facing cameras and then re-rendered for you in the virtual space. And then you can still adjust the rendering and you can add digital components. So it's really a integrated version of AR and VR from my perspective. And as you can see here, there's no clear boundary between different types of technologies. That is also why I will consider mixed reality as a whole spectrum together because they share a lot of similarity. For example, the integration of the tools. That also why we see that mixed reality might be something in the trend of like as a future interface. Other than the integration part, we also see a lot of potential out of the AR/VR mixed reality interfaces. For example, we can already find a lot of clues in today's applications. Mixed reality starts to change the way we have our entertainment, our social life, also some very important application scenarios. For example, the healthcare training, how to help the doctors perform an operation and other very important areas. But one thing is to mention is that the previous paradigm doesn't work, right? If you think about the difference in the interfaces, for example, if you are wearing a VR headset, you cannot see the outward physical world, then like typing on a physical keyboard, which is very typical and common if you interact with a desktop computer, it doesn't work anymore because you cannot really use your vision to detect which key you are typing. You can only rely on your muscle memory or spatial memory from there. So basically, that helps out like the paradigm we built for previous interface do not like really directly apply for mixed reality. So from there, we said like the challenge comes from the differences between mixed reality and the previous interfaces. We want to know what are the differences. There are many different aspects. I can only share some of my own perspectives. So from my view, I think there's two major differences. The first thing is the interface representation that is really different. So if you see mixed reality was able to actually connect physical world, digital world, and the human user to a level that no other interfaces was able to achieve because it has the sensing capability of making sense of the environment, has the sensing capabilities of monitoring the user status, and it can like do the UI adjustment and like placement considering all the factors so that it can adapt to different environment, adapt to different user status. And the second difference on the interface side is the avatar, right? So that's a unique thing we have as a digital replica of ourselves in the virtual world. So you have some virtual characters that represent you in the digital world. You can think the cursor we have on the desktop is like a 2D version of that because like where you put your cursor at like indicates your focus or attention. But the avatar itself is much more complex compared to the simple cursor, right? So it could be very realistic that you can think of like that is just like another version of myself. When I move, it follows my movements. But it can also be very flexible. It could be different from you in terms of the appearance, like the sweat, the skeleton or all the stuff, right? It provides some unique like interaction opportunities. That also will be something we'll talk about in the later of the talk. So one aspect is the difference in the interface representation, and naturally that will change the user's behavior while they're interacting with such interfaces. So not only the interface, not only the computer side, the user side is also different. As we mentioned before, like the input still here, right? Considering the user side, we'll talk about input and output direction. On the input direction, there are a lot of differences. For example, we rely on different modalities while we are interacting with mixed reality. It's very heavily on visual and different from like how we tap with physical keyboards. Nowadays, you face a trade-off between accuracy and speed because like most commonly we use like media tapping in a lot of applications. You either slow down the input speed by poke at different keys like carefully, or like you rely on your like blind tapping skills that will introduce more like errors. It's not only about text input, right? It's kind of an example of all the input tasks, thinking about like target selection, menu selection, a lot of things will have some similar challenges here. And also on the output side, how people perceive information from the computer is also different. That could range from like being overloaded or like being underloaded. For example, an example of overwhelming scenario is on the left. It's like imagine a world if so many different information sources are integrated into the physical world, we cannot really consume all the information at a time. We can be really overwhelmed. And on the right side is about the underloaded side, right? We can also be risky if we are not aware enough about the physical environment that we're in because of the isolation came from the digital world. So again, we found like mixed reality interfaces are different from the previous ones. There are unique challenges and also unique opportunities to take. We want to discuss what is the optimal interaction paradigm for it. So my short answer for that is that I still don't know. So basically, we are doing some research to approach how to optimize the interaction paradigm for mixed reality, and that kind of linked to the previous like concept model is like we need to rethink about this bidirectional communication between human and computer. I feel like there are a lot of behavioral changes we might anticipate, so that really requires us to gain a deeper understanding about how people perceive information with mixed reality interfaces and how that changed their mechanisms in like motor control and also the coordination between perception and motor control. Only with such knowledge we'll be able to augment our interfaces to better predict the user's interaction intents based on their input signals. And also we can determine what is the best display method to make sure users are not either underloaded or overloaded. And as a step further, we said there's so many different like unique opportunities to take. We want to also enable some novel interactions that is not possible without mixed reality. So from there, that come back to the title of this talk. What we try to explore is we try to first understand users' behavior in mixed reality, and then try to predict their intents in both like in input and output directions. And finally, we want to enable new interactions. So I will go through a very brief walkthrough of some of the projects I did before, and then I will walk you through some projects with more details. So as the basis of my research, I conduct several like user studies, try to model the behavioral patterns of users while they're interacting with digital contents in mixed reality. Some examples, we try to measure how people will point to different locations without the involvement of their vision, right, in an S-free manner. And also we try to model how people will map the object they want to interact with a grasping gesture metaphor. And then we'll try to model the perceptual like the perception accuracy, precision about depth with like artificial cues. For example, if we introduce the color of the appearance as a depth cue. And based on this like knowledge about the user's behavioral patterns, we build interaction techniques to facilitate the users in both like input and output tasks. For example, we build multimodal interactions leveraging the user's head movements, hand gestures, and also facial expressions to make them like the task easier for them to input their interaction intents. And I also build adaptive user interfaces that consider the environmental factors and also the user's task, user's cognitive load, then try to optimize the display method to make sure users have enough information for their task, but also avoid them to be like overwhelmed. And step further, we try to explore some more crazy ideas about whether we can enable something that is not possible in the physical world. For example, can we embody people into non-humanoid avatars? Like, can we embody people into like digital elephants or like different animals, right? So there we try to explore a few interesting ideas. And that actually forms two threads of my research. If also you can think about as a 2x3 metric. It's about how we can understand, predict, and enhance user behavior on both input and output directions. So I will go through 6 projects, might be too much, but I won't provide like the similar level of details. Probably I will only talk about an avatar, which is relatively the most recent one with more details. So on the input side, we start from understanding users' input behavior patterns, and then we start from like understanding their single individual touch points. So here is a example scenario, right? So one motivation of this project. So in this project, we try to explore how people perform as-free target acquisition in the world, in the space around their body in VR. And the motivation is very straightforward. It's because like avoiding rotating your head a lot, that will help you reduce some of the motion sickness. As a brief background, the motion sickness, a theory based on sensory conflict mentions when you see some conflicts between your visual perception and proprioception, you'll feel like motion sickness. That's similar when you're drunk or opposite, right? You see the world is rotating, but your body is telling you, no, you're standing. So that kinds of conflicts indicates you should get things out of your body, right? So that is the motivation. What we want to see is like without looking at the target, only based on your spatial memory and sense of proprioception, how precise can you perform the target selection, and can we compensate for the imprecision with some prior knowledge on your like behavioral patterns? So another perspective for the motivation is that previously on the other interfaces, we have a comparable like input and output space. For example, we have the screen-sized output display space, and then we have a table-sized like input space. And then in AR, VR, our interaction space has been extended to the whole space around us, or even more. But our visual perception space is still limited. If you are familiar with like AR, VR headsets, it's still like 120 degrees or even smaller. So without that is the time to actually disentangle visual perception with motion-based interactions, right? So that's the starting point we try to explore. Can we just let the users try to select something in an as-free manner without looking at the target? And then that causes this challenge, right? For example, if I'm doing some like 3D modeling or designing work, I want to reach out to a tool at hand where I roughly have the memory about where they're located at, and then I just reach to the location without looking at it. As you can imagine, because there's no guidance from the vision, there might be some errors, right? For example, if I want to reach to one of the objects, I probably will reach to somewhere in the middle of the two. So that kind of causes the problem for the system, for the interface, how to interpret this into input behavior, which of the two objects the user is actually wanting to select. And to address that, we believe knowing more about the behavioral pattern might help. For example, if you only have a single observation about the input behavior, that might be challenging. But if you observe the users to select the target multiple times, then you can kind of gain the knowledge about the distribution, right? You might see a pattern. For example, if the user wants to select the point in the middle, and with a lot of like trials, we will see the distribution of the actual average position with the offset to the target location. And then you can also model other parameters, for example, the standard deviation. With that, you can estimate the probability of the users wanting to select this target based on their endpoint. So to achieve that, we actually do the data collection. I will just like briefly go through that. So we place the target at different locations, and we ask users to select them without looking at them multiple times. So we kind of collect the data. And then from there, we can actually know better about their behaviors. We can try to find the patterns. For example, when we place the objects at different patterns, so here is like angular space, right? It's like the horizontal angles and also the elevation angles. So we place the objects at different places. We see there are patterns, right? If we move the target from the middle to both sides, actually the offset between where the users are expected to locate at and their target location, the offset has a pattern, so it goes downwards and with a larger amplitude. And something like that, with the sample data, we were able actually to interpolate for a model that can captures. Once we know the users want to select a target in the space around them, what is the expected location they will reach to, and what is the expected standard deviation? That is very useful for us to compensate for this like imprecise input behavior. We use the same example here. If we, based on our data, we know if the user want to select the magnifier, it's more possible they will reach to somewhere like on the right. And then if they want to select the scissors, they actually goes to the bottom left corner. From there, we can use any kinds of inference technologies. It's easier to let the system to know. In this case, the user is more possible to select the magnifier instead of scissor. That's a simple illustration of how it works. We actually did an evaluation study, but I will just skip that. So that is the first project. We try to analyze a specific scenario when the users want to say something without looking at it. That is very helpful and also uniquely needed in mixed reality. And then from there, we try to extend that from two perspectives. The first is like, instead of just thinking about single touch point, we want to know what is the behavioral patterns of the user's arm motions. And then another difference is like, instead of try to compensate for the imperfect input behavior, we try to make the input behavior imperfect. So we try to add some offsets. So in this project, what we did is like, as we said, we have an avatar that represents us in the digital world. And actually, the behaviors of the avatar and the physical human could be different. It is not necessarily they need to as accurate as like the same. That is not always the goal, right? So here we want to test if we injected some offsets between the motion of the physical arm and the digital arm, how possible the users will notice that. And then if the users cannot notice it, can we leverage that for some applications? So here's another illustration of the basic concept is like we sense the physical arms pose, right? We sense the motion of it. And then in the digital world, we want to inject some like offset. For example, we rotate the joint of the elbow or the shoulder that creates an offset. And based on this direction and strength of offset, we want to predict how possible the users will notice that. And then why do we want to make sure the users are not like the offset are not noticeable to the user? Because with such a difference, we can make something like interesting. For example, in the rehabilitation task involving like arm motion, in the physical worlds, people may get frustrated because they cannot reach to the location they were able to reach to before, right? But in the digital world, in the virtual world, we can somehow makes you feel like your body is healthier, right? You can reach to somewhere higher than your physical body can. So with such, we can create the offsets and to make the users more engaged on these tasks. There's a follow-up work that not done by me, but they actually deploy this kind of mechanisms in the actual hospital, and that was published in the HCIL last year. So the basic task of our paper is try to predict the notability of the offsets with different strengths and directions. We go through 3 different studies step by step from the simplest version to more complex scenario. But the tasks for all the 3 studies are the same. So in VR, we show a target pose, and then we ask users to move their arm to align with that target pose. And then during this process, we introduce a rotation offset, and then we ask users to help us label whether they perceive something different, try to help us improve the tracking accuracy. We actually tell them the actual purpose after in the deeper session. So I will also like skip most of the details of the study, but we start from somewhere very simple. So we only apply offset on single joints with fixed directions, and then we try to model what is the like probability of users noticing the offset based on their strengths, similar to the S3 thing. We just like model the whole thing, and then we go to the second step. Basically, not only we still apply the offset on the single joint, but we try to vary the directions, right? We try to test how direction of the offset will make a difference. And from there, we feel like actually it doesn't make a very, very significant impact because all directions form like a corner line roughly as a circle. And then we try if we apply two different offsets on two joints with different strengths, with different directions, how they interfere with each other. So we were able to see a significant interaction effects between the two offsets we apply on the two joints. Simply saying is that like applying an offset on one joint will push the counter line of the other offset on the other joints to the opposite direction. Basically, they're compensating for each other. So from there, we collect the data. We kind of like know the pattern of the users. We leverage that knowledge to build up like an algorithm to calculate the dynamic offset we can apply that is not noticeable to the user while they are moving their arm in the virtual world. So leveraging that, we build up 3 demonstrative applications to showcase in different scenarios, people may have different requirements about noticeability. For example, for very serious tasks, for example, rehabilitation, we want to make sure the user feel like that's their body. Otherwise, they will just like give up the task. So we can only apply a small range of offset. And then there's something in the middle, for example, some game, you can simulate different body types. If you got a virtual gunshot, we can move your arms slower than you do. Then that can simulate the feeling of injured body. Or if you have a energetic body, we can make your virtual arm moves faster than your physical arm. And then in a very low priority of noticeability is the productivity oriented task. For example, you are doing some task, the efficiency or like the task completion is your highest priority. You can bear some kinds of like offset as long as it's beneficial for a task. Yeah, so that is the second project. We extend from one single joint to a couple joints, capturing your arm motions patterns. And then instead of like just like compensating for the errors, we intentionally added some errors to the motion. And in the third project that we'll talk with most highest level of details is we also want to make things a little bit more complicated. For example, can we just consider the whole body skeleton difference? So instead of only changing motion, the motion part of the avatar, can we change the structure appearance of the avatar? And then instead of considering one or two joints, can we consider all the skeleton joints on the human's body and also on the avatar's body? So that comes to the third project. We kind of introduce a new embodiment techniques called hand avatar, where we allow users to embody non-humanoid virtual avatars with their hands as a puppet. So I will show you some examples here. It's moving. Okay. So with this, we were able to let users to control a virtual avatar that's so different from a human. You can actually embody into an elephant or a bird or like a spider with one or two hands as a puppet. You control the motion of every joint of that avatar with the motion of your finger joints. And as you can imagine, it's kind of like it's doable for us to manually design the mappings. But if you want to see, that also takes a lot of time. So also takes like expertise in the design and also like sensing technologies. What we want to do is to automate this process. So once given a virtual avatar skeleton, the algorithm can automatically optimize the mapping between the two. So I will go through like how do we achieve that. First, let's define what is mapping, right? What is mapping between the hand joints and the avatar joints? Basically, its function is like given the hand pose of the user, it can relate that to the motion of the avatar joints, right? Once you change your hand pose, it will be reflected in the change of the pose of the avatar. And what is included in this mapping, we consider two basic components. The first is the starting pair of the avatar pose and your hand pose. So without any manipulation, what is the starting hand pose? What is starting like pose of the avatar? And then from there, we need to determine the relationship, the connection between the hand joints and the avatar joints. So which joint you are moving will trigger the movements of which joints on the avatar. From there, with both, right, we can actually keep tracking of the hand movements and apply the difference to the original starting pose, and then add that, translate that to the delta you need to apply on the avatar pose, then we can generate the animation based on that. So in this project, we also go through 3 steps. The first is try to conduct user study, try to observe, because at the beginning, we really don't know what people are looking for while they're controlling avatars. We want to know what is the definition about a good hand to avatar joint to joint mappings. So we did the observation study, try to learn the user's perspective, what they value about this mapping. So we had two phases in this study. Actually, the first is the design phase. We invite people to design the mappings themselves, considering different like characters, different avatars. They can generate their own mappings between the hand joints to the avatar joints. And then in the second follow-up phase, we asked them to try out different designs, both designed by themselves and also designed by others, and try to vote what is the best mapping and share with us the considerations. So this is the interface we use. This way you can define the starting reference, and then you can link different drawing points to different drawing points, create a mapping. And then we ask them to try out the designs by themselves and others and try to use it and try to give feedback about what they care about. From there, we gather some useful insight from the users. For example, as the highlighted numbers here shows, it's like most of the people don't prefer their own design, so they favor others' design. It's kind of an indicator of like they cannot really do the design by themselves. Either you always have a group of people there to design a thing for them, or we can also build up an algorithm to automatically generate the mappings for them. And then the second thing is like people are quite consistent. They reach a good consensus about what is a good mapping. They commonly commented on 3 dimensions. That is the control, how easy it is to control the avatar motion and intuition and comfort. From there, that's the guidance we use while we are building the system. So that leads to the second part is the implementation part. Basically, we build up an optimization algorithm to take care of the design process. And the optimization algorithm takes as input 2 different kinds of knowledge. The first is some knowledge about the hand. So for example, the range of motion of each joint, that's something people are very, very similar. So we can gather that as a prior knowledge. And also the similar information about the avatar joints, what is the reasonable pose, what is the range of motion of each avatar joint. From there, the output of this algorithm is to determine the mapping. The mapping consists of 2 parts, the reference pose pair and the joint mappings. And we have 3 constraints to maintain that helps us to reduce the search space and also just like try to align with the considerations we gather from the observation study. The first thing is we constrain our mappings to be 1-to-1 mapping. So only the movement of one joint on the hand only triggers the movement of one joint on the avatar. M2 mapping might be interesting. We leave that as future work. And then we also keep the hierarchical order the same on the 2 parts. So we only map the parent joint on the finger to the parent joint on the avatar relatively, right? And then we also keep the balance constraints. It's like when we design by manual or 2-hand designs, we make sure like not all the joints are located on a single joint. So we keep a balance ratio. From there, what we do is like we construct this objective function to reflect what users actually value in this mapping. So we come up with a computational method to calculate the level of comfort similarity that's a proxy for intuition. Is more similar, the control is they feel more intuitive. And also the actual control, the ease of control. So we apply different metrics. For example, for comfort, we calculate the ruler scale. That is an established scale measuring how comfortable the pose are. And then the similarity, we try to calculate the motion difference between the hand and also the avatar to make the more similar, the people feel more intuitive and natural. And the control is like we already know the range of motion of the finger joints and the avatar joints. We try to calculate what is the overlap between, based on this mapping, what is the overlap between the hand joints range of motion and that of the avatar joints. The larger overlap allows you a bigger space for control, right? That's make the control easier. So we don't go into details, but ideally, based on this objective function, what we want to do is try out different combinations of the mappings and try to find which combination will maximize the value of the objective function. But actually, it was extremely difficult to exhaust all the combinations if you think about different mappings, different like starting pose, right? So what we did is actually so here I want to give you an illustration about like both the mapping and the pose pair will impact. If you just so here how we control the animation or the motion of the avatar is like we have a pose pair as a starting point, and then we capture what is the relative difference of your hand pose and translate that and apply that onto the avatar, right? If you just change the pose pair from pose pair 1 to pose pair 2, that is the first 2 rows, you will have a different hand poses, but they will have a consistent delta because that only is the delta between the starting hand pose and in pair 1 and pair 2. But if you also change the mapping, the difference between the hand poses will also be interpreted, it will also be converted as a different delta on the avatar pose that will lead to a very significant different change. So that is a little bit motivational about why we need to do the simplification. So what we did is actually a simplified version of optimization. We try to use some simulation. We gather a set of avatar pose that is reasonable, and then we gather like a set of hand poses that are comfortable to perform, and then we use all combinations of these as a simulation of the actual pairs. And then based on this data set, we try to optimize the mapping, the joint-to-joint connection in the first steps separately. So from there, we can generate the estimated best mapping, and then we try to run the actual optimization again to determine the starting reference pose. If that's too complicated, we can skip this. All the details are in the paper. So anyway, we were able to make sure the optimization works so that we can actually, given like any kinds of like avatar, we can generate a hand mapping that allow you to embody on that avatar. And to make sure it actually worked as we expected, we conducted a technical evaluation. It's not a real evaluation because we built up all the algorithm based on the data set. But we want to verify, for example, we have 3 dimensions, right? The comfort, the control, and similarity. Based on our optimization algorithm, hand avatar was able to generate the mappings that outperform user-voted and also user-generated mappings in all 3 dimensions. So it's in the front, top, and right region of all the results. And then we also want to perform some actual like evaluations. We go through application and also a comparison study with a baseline. So in the comparison baseline evaluation, we try to compare 2 aspects. The first is the control precision, how well you can control your hands, your avatar, and the second is whether the overall user experience was improved. So we tested 2 different tests. The first is like we ask users to mimic a target animation. So that is allows us to compare control precision. The second is like an open-minded. It's just like a composer animation that you are interested in. It's a creativity relevant task to evaluate the overall user experience. So the baseline we compared, we call the body avatar, is basically a body-based mapping that is applied in a lot of research papers and also applications. So we just compare hand avatar with body avatar. The result parts are the most boring part. So basically, there are some pros and cons about both methods. For example, without moving your body in a large scale, it saves your like physical efforts. And of course, you need if you are controlling them with your hands, which is more how say you have press control, so some precision metrics are better. But as you can imagine, for example, embodiment would be something you don't have a significant improvements because like it's always a natural mapping between your whole body with the whole body of the avatar. And then something interesting is we try to think about like what kinds of applications might be beneficial or might benefit from hand avatar. So we build up some demonstrative applications. One thing we thought about is like we are communicating with other people in the format of human, but in VR that is not a necessity, right? So for example, in a social scenario, can we embody in different animals? How that change our behaviors? Will that like foster some interesting discussion with your friend? For example, if your friend is an elephant and then you are a crab, right? And then we also think about something more relevant to creativity. Can we build up some tools for the designers or like the content creators? For example, we also integrate some like shortcuts, for example, some gestures. Can we make that as effective tool? They want to generate something to produce some 3D animations in VR. And then we also want to extend that to the control of the whole environment, right? We only allow the users to control a character, avatar with their hand, but they have other body parts. Can we also control the whole environment? So for example, if I'm a director, if I want to test out some things in VR, can we just prototype the thing with myself? That's kind of like a prototyping tool. All right, so that is the first line of my research. I don't know how much time do I have, but basically we try to explore how we can understand user behavioral patterns and then try to predict their noticeability of something we added. And then we try to explore the space whether we can do some novel interactions with VR on the input side. And then also it goes from the single joint to 2 joints as an arm motion and to the whole set of the body joints. I will briefly go through the other direction then. So it's kind of on the opposite side, how we show people the interface to facilitate them in different tasks. So all things start from also, that's my very first published paper in my third PhD year. I was very anxious at that time. All right, so it comes from the actual thing is try to strengthen the connection between the physical objects and the digital elements. So what we propose is that we already know how to gesture a physical object. For example, we use some grasping gesture to describe the thing we refer to. Can we transfer that to the virtual space, right? What we do is like we try to link a grasping metaphor that helps the users to select the virtual elements with this kind of like gesture mapping. And then if you look back today, in a lot of games, they just apply very similar things. I mean, it's a straightforward idea as well. So basically, it's like try to leverage the semantic connections between the virtual elements with the physical objects. So how to achieve that? We need to understand how people actually perform this grasping metaphor, this grasping gestures. So what we did is just like run an observation study, right? We ask users to perform grasping gestures, and then we can kind of like generate a mapping between the object and the gesture. And then very straightforward, we just like collect the data, analyze the data, and we found that what people think about in this like mapping is like the gestures are related to the shapes of the objects, the usage of the objects, and also the size, right? From there, we'll build a very easy, very simple like machine learning algorithm to classify which of the objects users are gesturing. So that's a really straightforward idea, but that's where we started to think about the strengthen the perception of the users in the digital world, how we can leverage some of the semantic connection to the physical world. And that leads to the same direction in the second project. Instead of consider the connections for each element, we are thinking about the whole layout. Can we optimize the display of layout of interfaces, leveraging some connections, some semantic connections between the physical and the digital? So here in a imagined scenario, we will use AR and VR, especially AR, in our daily life tasks frequently. For example, I'm writing a paper in different physical environments. I can write a paper in my bedroom, I can write a paper in my office, or like in a quiet cafe, right? But the task is the same, so that requires the same set of user interfaces to help me with the task. But if we go to a different environment, I need to manually rearrange all the 3D elements again. That's really very tiring task, right? It's kind of annoying. So we want to see, can the system automatically adjust the layout based on some semantic connections between the physical objects in the environment and the digital contents we need based on the task. For example, we can always place a calendar to the clock. We don't have a clock here, but because they share the connection to time, right? If you want to see what is the next event you need to attend, you turn back to your wall to the clock, and then you also see your digital calendar. So that is the basic motivation, and the task for this project is to predict where the user want to locate the digital interfaces in the physical environments, right? And similar to virtual graphs, we did an observation study, right? We just observe, we put the user into one environment, ask them to design all the layout, and then we move them to a different environment virtually, and then ask them to adapt the layouts for the second environment. By comparison and considering some like external validity, we try to use different scenarios, environments, right? And then by comparing the designed layout and the adapted layouts, we want to see what are the things users want to maintain in different environments in these layouts? What are the factors they care about in these layouts? So from there, that we kind of like focus on the semantic connections and also some requirements, for example, visibility, whether you need to reach to the objects, right? That guides our implementation of the algorithm, which is very similar to an avatar, so I will skip it. So the algorithm, we take the scanned mesh of the environment, also the objects labeled, the potential space we can place objects labeled, and then we have some predefined utility scores, and also like usage requirements, and also the semantic associations to the physical world. And then we voxelize a host space that's kind of the containers where we can put the interface in, and then we solve this assignment, right? Which objects to which location as like a linear program. So similar to hand avatar, we just come up with an object function to represent users' needs in different dimensions. For example, the semantic agreement and also like interaction requirements, right? In a computational way, so that given the input, we can actually automatically generate a layout that optimally help the user in their tasks. And then from there is kind of we're still working in this direction, right? Based on this optimization, we can do a simply one-step adaptation from layout one environment one to a second layout in a different environment. But we're also thinking if the user are really using this kind of adaptation tool, how we can model their changing behaviors in different environments in a longer period of usage. All right, that is the second project. So we think about from the element to the layout. The next step we are thinking about is the whole environment, not only the interface, not only the layout of the interface, but the overall rendered environment in the virtual space. How we can enhance users' perception of the whole virtual environment with some computational methods. So here we focus on a very specific challenge is the depth estimation issues in VR. As you may know, right? People may underestimate the distance of the objects from the objects to the user because of some rendering issues that is not perfect. And then one way to reduce that issue is try to integrate as much as precise depth cues we adopt in the real world. For example, we have a lot of depth cues we rely on in the physical world. That's our first nature depth cues. For example, the relative set, occlusion, and also the motion parallax when we want to focus our gaze on something, right? The muscle of our eye around our eyes will also provide the perception cues. And then here, what we want to explore is that instead of only trying to integrate as many cues as we already adopt, can we invent some new cues that is possible or supported by mixed reality, right? It doesn't need to be the cues we rely on in the physical world. So thinking from that way, there are different designs here. We want to explore a single example is, can we use the color of the object's appearance to reflect the depth from the object to the user? And then we choose color is not a really random choice because like mapping colors to different things is kind of a common practice. It can reflect the atmosphere or like emotional affective status of the user, or directly you can apply color to depth mappings. But here we want to emphasize that we are not choosing the hue of the color to reflect the depth because like hue is not really doesn't have an order, right? You cannot say like green is bigger than yellow or like red is bigger than blue, right? But we try to use the value and also the saturation as another two-dimensional color to map to the depth. So here's the concept, right? Similar to how we did the other projects, we try to find a computational way to determine which depths the color can indicate for the users to recognize. And from there, there's this one like, for example, if we want to indicate the object is like at 0.35 meters from you, which color should we use to change the appearance of the objects to indicate user of that? And then we face a trade-off that we need to think about is the trade-off between number of depth levels we can have, and the other is the confusion probability. I can explain a bit, right? If we have a lot of numbers of different cues, so we can help the users have a better precision of recognizing the cue, then they have like a better resolution of the depth perception. But on the other hand, if you have too many cues, then you might use some colors that is easily confusing to the user, right? They might misrecognize a couple of the color cues that also lowers the precision, right? It's kind of they might mismatch the colors with the depths. So we want to find a sweet spot where like we can have a good balance between the two. What we did is very similar to the other objects, is try to observe how users map them, and then based on the data, we try to calculate what is the best solution, best mapping between the colors to the depths, and then eventually we do the evaluation. So the first two parts we have repeated a bit. We focus on the evaluation. I want to show you the effects. So we choose the 3D sketch as the task we used in the evaluation because that requires both input and output side, right? It requires users to first observe the structure, and then they need to rely on the visual guidance to perform the actual sketch. And then we also tested 2D, 3D, and then we use like normal metrics on completion time, errors, and also collected their behavior, like a subjective feedback. And then, like, as you can imagine, adding the color as a cues may performs better in terms of precision completion time, but also requires heavier mental load. And then we try to think about, with this color as a cue, can we augment users' behavior in more applications? So we think about some demonstrative application here. For example, in an augmented reality scenario, can we just like help users to avoid obstacles while they're driving? Although this video is shot by actually where we were walking, but we try to simulate if you are driving, and then we can actually give you a heads up about the depth of the obstacle that might be helpful for you in the real life demonstration, navigation, sorry. And then on the second part is like, if we can get the users have a better estimation of the depth, probably that that it will improve the precision while they are performing these sketch-based gestures, that will allow the system to have more instances to support compared to without it. And then we come back to the same like layout adjustment. If you really want to play something at a very close depth from you, you can use color as a cue to group them that have a better alignment in the 3D space. And for visualization, you can still use color as cues to have a better understanding of the spatial relationship of the data points. All right, I think I'm close to the time. So that is the second line of my research. We start from like thinking about the single element to the whole layout of interfaces, and then try to enhance users' depth perception about the whole environment. With that, I will conclude the talk. Is kind of I try to share what we did in this little space about like how to improve, understand, predict, and enhance user behavior on both input and output sides. No, thank you for attending the talk. I'm open to any questions.